Today we're going to be designing a water piano in Fusion 360. The water piano is a classic 555 timer circuit, sometimes called the Drawdio, and Rob Mosslinger at Walnut Grove Secondary School brought it to my attention because his students were having just a great time with this thing. Kids who are at the least bit musically talented can actually create some neat songs with it, and those who aren't can just be really, really annoying, which seems to please them as well. So anyways, I've got a web page up with more information on the Drawdio, or water piano as we call it here, and that is at botshop.wordpress.com. So botshop.wordpress.com. So if you Google the water piano and bot shop, it should take you straight to this page. And on the page, I've got some information that I'll delve into in a little more detail in a minute. But in a step of meta, here's me showing you a video of me showing a video.
Okay, here we go. This is the water piano, sometimes also known as the Drawdio, a little 555 timer circuit. One end of the circuit goes to the aluminum case, which is sitting in water, and we've got a trail of water coming along right here. And the other end of the circuit comes out to the clip right here. I hold that in one hand, and then I come down here and with my other hand, how do I do this? Holding on to the phone. Just a minute here. Take my other hand and touch the water. Oh, turn the circuit on. Turn the circuit on there, teacher. The closer I am in the water, the higher the pitch, the further away. That's really annoying. I should have had someone hold the camera for me. Anyways, you can make some great sounds with it, and kids who know music figure out to do a lot more with it than I do.
Well, there we go. How exciting is that? Somebody shows you a video while you're watching a video. There's a few other links in here that are useful. So this is where you can come to find the schematic. And the schematic will come down as a PDF file. And so you can take a look at it right here. And it's got the 555 timer chip right here in the middle. I'll come back and talk about the schematic a little bit more in just a moment. But what we also have in here is a link to the water piano simulated on falstad.com. Now, falstad.com is this really cool website where a guy named Falstad puts up a bunch of cool simulations that he's created. But if you go to falstad.com/circuit, it will take you to his circuit simulator, which is an amazingly easy to use free piece of engineering software. It's unbelievable that this is available for free on the internet and has been out here for years. And so let me just take a moment to talk a little bit about what's going on in the circuit right here. We've got our battery over here, and we can right click on that to set our battery voltage. It's running at 9 volts. Here's our 555 timer in the middle. On this side where the schematic shows a speaker, I've just thrown an inductor in there, just a little coil of electricity, because that represents kind of how a speaker would behave. It is a coil in there. There's a bit of a resistance in there too. I should probably put some resistance in line with that to be even more accurate, but this is doing the trick, because what we're seeing is we're seeing the sound come through down below here on the oscilloscope, and I'll talk a bit more about that in just a moment. Over here, I've got the two terminals, one that would normally go to the case and rest in water. The other one would be the one that you hold on to, and the resistance between those two terminals would vary depending on how far away your hand was in that stream of water. And so what I've done to replicate your body resistance and that stream of water is put a 5 megohm variable resistor in there, and you can play with the value of the resistor by coming over to this side of the screen and sliding the resistor off to one side. There we go. And you'll notice that as I slide it off to this side, this is like taking your finger and putting a long way away from the circuit. The peaks between these waves right here get further apart. And I'm just going to stop that for a moment so we can take a look at it. And what you'll see on here is you can actually come down here and you can time the time between the peaks right here. So from the beginning of this wave, is that one starts at 2.256 seconds, and this wave starts at 2.261 seconds. So you can calculate the peak to peak interval, and that can give you the frequency of that wave. Now, what's interesting is that, of course, being a computer, it's calculated all that for us. And what we see down here is we see the peaks all being represented in red on the frequency chart right here, and our primary frequency is sitting right here at about 191 hertz. So that would be a lot. That would be an audible sound coming in, very audible, coming off of a small speaker. You'll also see a few little harmonics of that right in here as we come along, but our primary signal is at a couple hundred hertz. And that's because our finger is a long way away. It takes longer for the circuit to charge back up. It takes longer for the 555 timer to pulse the speaker. So we hear a lower frequency sound. Now, if I bring that resistance down lower, okay, and let me run that again. Well, now you can see that those peaks are all very close together. And we'll just stop that and take a look at it right in there. And you can see that now 2.379 seconds and 2.38, we're talking about very tiny, tiny times from peak to peak on there. And if you look at the peak wave frequency that we see right in here, that shifted up from 200 to about 3000 hertz or 3 kilohertz right in here. So looking at the red lines, and at the peaks right in there, you can see some of the harmonics tucked away down underneath right there. So as we vary that resistor, we see different frequencies coming out on the oscilloscope, and we would hear different frequencies coming out on our speaker if we were running that. So falstad.com/circuit, very, very cool circuit simulator, fairly easy to use. You just come in here. He's got some sample circuits for you to use, so you can get in. You don't even have to design your own circuit to get active on it. And when you do want to design your own, you just create a blank circuit. You right click and you start adding the parts that you want. It's probably one of the easiest to use electronic simulators that you will find anywhere. But I'm going to go back to the web page we were at. And so that's the water piano at Building Robots at School, botshop.com. And we'll just move that off of our screen right here so we can switch over to Fusion 360. Now I recommend that you go to that site and download the schematic. Here's the schematic that we're going to be using right here. And before we get into it too much, for those of you who are new to using electronic CAD, I wanted to point out something about these ground symbols. Sometimes people get a little bit confused and, where do I find the ground symbol? What does it mean? Well, anytime you see a ground symbol, or sometimes you'll see a triangle that's flipped around and pointing upwards that says +9 volts on it or something like that, that's telling you which net that pin is joined to. So that says this pin right here is joined to the ground, or GND, net. And this pin coming off of this capacitor would be joined to the ground, or GND, net. And same here right here. So effectively, you could just come in, and instead of having this all be separate, you could just come along and draw one big line right along right in there. Let me see if I can draw that. And it's not going to let me. I don't have the fancy oh, there we go. Do I have a fancy enough version of? So you could just pretend these are all connected together right like that with one line. And so our batteries connected here, those are all connected together. And the reason that we don't do that is that on some circuits that gets really crowded when you start trying to connect all the grounds together. And if you just say this line goes to ground, it expresses the concept that you want without having to draw a whole bunch of complex lines and have people track the line down and say, where does that line go? They just take one look and they say it goes to ground. Now on your printed circuit board, you do have to have one piece of copper connecting these all together. They do all have to be joined to each other because they all do have to be at ground. But Remember that schematics are about telling the story of the circuit board, and you want to tell that story in a clear and easy to read fashion. The circuit board is about implementing that story, making that story happen, and that's where things get a little bit trickier sometimes. Okay, download a copy of the schematic, put it on your other screen, and that will guide you as we go through and create our schematic right in here. Before we go and start creating that schematic though, I want to take a moment to talk to you about libraries because I've ran into a few library parts that I don't really like in the libraries that Fusion 360 has available for you. And if you'll recall from our previous tutorial, one of the challenges is that some of the library manufacturers have been using the polarized capacitor symbol for their non-polarized capacitors. Okay, they just shouldn't have. There's no reason. It's easier to make the non-polarized symbol. So let's take a look at how we might make our own capacitor, and we'll put it in our own library, and then we'll carry on from there. So before we get started making our circuit, we are going to create a new library. So go into Fusion 360 and go ahead and get your documents open. Make sure your folder's in whatever folder you're saving all your electronics projects into. And let's go ahead here and under File, we're going to go New Electronics Library. And you should get a window come up that looks something like this. And as I like to do with all of my files, as soon as I bring it up, the first thing I'm going to do is save it and give it a file name. And I am going to call this one I need some, psyching up here, keep my energy level high. I am going to call it an awesome library. Feel free to use your own adjectives. I hope you're feeling awesome too. Okay, so what have we got in here? So the content manager is where we're going to put all of our parts together. And an electronics part consists of 3 or sometimes 4 different things. The symbol is what you see on the schematic. So the symbol is your schematic symbol, and you can see there that's actually showing you a symbol in a couple of different colors. Your footprint, well, you can see that kind of looks like a surface mount chip that would be showing up on a printed circuit board. So your footprint is the actual physical size that that goes to. Now, one symbol can have multiple different footprints. So if you think about a resistor, for instance, you can have a surface mount resistor, you can have a very short resistor, you can have the resistor kind of stand up on end and bend over so that you can tuck it into a small place, or you can have a resistor with really long leads on it so that you can run a whole bunch of wires underneath it. So one symbol can have multiple different footprints. And sometimes one footprint can be used in multiple different symbols. So if you think about the footprint for a transistor, you might use it in a PNP transistor, or you might use it in an NPN transistor. So what we need to do is we need a way to keep our symbols and our footprints together and organized, and that's where we have devices. And what the device does is it links a symbol to a footprint, and it says which pin on the symbol connects to which pad on the footprint. Okay, pads are your copper implementation of the logical pin that we have for each symbol. So if you've got something like a resistor, it will have 2 pins and it will have 2 pads. And it won't matter which way they're hooked up because it's not polarized. But if you have an integrated circuit, you might have 8, 16, 32 different pins right here, 32 different pads down here, and it's sure going to make a big difference that you get them hooked all the way the right way around, and the device is what keeps track of all that. Fusion 360 also has something called packages. Because Fusion 360 is a 3D design package, you can use the package maker to create a 3D version of your part, and that when you look at your circuit board in the 3D view will actually have a life-size, very nicely rendered drawing of your part in there as well. This can also be used to help create footprints because the footprint is linked to the 3D package. All right, let's start by making a symbol, and we're going to create a symbol for a non-polarized capacitor. So what we're going to do is we're going to come up here and we're going to click on that plus sign, and it's going to say create new symbol, and we're going to create a new symbol, and we are just going to call this one cap. And here we go. Now we've got a drawing space right in here where we can draw our capacitor, and you'll see that we're drawing on the symbols layer. All right, so a capacitor is fairly simple to draw. What we're going to do is we're going to start off by adding the 2 pins. Now the 2 pins are eventually going to be connected to our 2 leads going down into the circuit board, and this one's not polarized, so I'm not going to be too fussy. But let's bring that in right here. Now I'm just going to zoom in a little bit so that you can see they've got a funny color choice right there. They've got gray on white. Okay, and not the color choice I'd necessarily choose for a capacitor. And I'm going to put that pin in right there. And then I am going to rotate it and put it in right about there. And now I've got 2 pins right in there. You can see them represented, pin 2 on that side, pin 1 on that side. And I'll click on the OK button to get rid of that. And now I'm just going to draw a couple of lines in here. And I'm going to draw those lines so they come down here and look relatively symmetric. And actually, I'm just going to click OK. And I'm going to draw another line right here and bring it down right to there and say OK. And so there's my capacitor. Now you'll notice the little crosshair right in the middle. That's the origin. When we install that point, that's the point that we're going to click on that to move it around and adjust it and do all sorts of things like that. Now, the other thing that we should add to this is a name and a value. And to do that, click on the text, and the text box pops up right here, and you enter the text. And to have the name and value automatically show up, you start with the less than sign, and then you say you want it to say name. Just put it all in capitals, and we'll put it right up here. Of course, you'll be able to change that later on. Oh, let me undo that. Control Z. I made a small mistake right there. We're going to put name in there. But I almost forgot we should put that on the names layer. Let's move it over. Yeah, it'll do fine right there. And then after putting name in, we are going to put value again in all capitals and on the names layer. Okay, so when we go and put that circuit onto our board, if we tell it to say C2 and 10 microfarads, that's where those values should go. Alrighty, so that's been drawn right in there. We've got cap right there. Now it's still showing us no pins. I'm just going to leave it like that for right now. I think it takes a moment for that to update. We have to come along and do something with it. Let's come over here to footprints and let's create a footprint to go with it. And we're going to create a new footprint right here. And I'm going to call that footprint. This will be a plastic cap underscore film, plastic film capacitor, which is good for our small value non-polarized capacitors. Now, we had 2 pins on the schematic. So what we want to do is we want to create a through-hole pad right here. And so if I click on that, you see I've got some options in here for my for my hole shape. I'm going to go to a round shape, and we can control the diameter of that. I'm going to bring it up a little bit, and I like to have, somewhere I calculated this about beforehand, somewhere in the neighborhood of, if we can bring that up, the whole diameter. So this is the whole diameter we're looking at right here. That comes through to right there. I like to have that somewhere in the neighborhood of about 30 thou. That's a little bit small right there. And you can see that the annular ring is looking a bit small. We'd like to bring that up. See if we can make that a little bit bigger. if we can give students a bit more meat, then they're going to have an easier time soldering that into their board. And most of the film capacitors that I have, they've got about 300 thou in spacing between their pads. So I'm going to put one on this side. I'm going to start here at the origin. I'm going to come up 1, 2, 3. That's 150 thou above, and that's where pad 1 goes. Then 1, 2, 3, and click. And then I'm just going to say OK. And that is the spacing of a lot of the small film capacitors that I've got in my shop. And now what I'm going to do is draw a line to go right around them and indicate the footprint. And that goes on the T place layer. And we'll just come in here and draw nice little box like that. And that should let us know that the capacitor is going to be properly spaced onto the board right there. Now we can also come in here, and if we want to have the name show up on the top layer, we have, where are we here? We've got a names layer on here, T names, top names. And what we'll do is on the top layer, we'll put name. Oh, don't click OK until you're done. Name. We'll just put it off to the side. And then we'll put value. Okay, that's looking good right there. So when we go to make our board, we're going to have those two pads that we can route to, and we're going to have this much space set aside, and we're going to have the name and the value show up on the board if we decide that we need it. Okay, so let's see. Now we're going to come over to devices right here. Let's see if I just come back here. Yeah, it just wasn't updating in there. It knows that my symbol has two pins, that my footprint has two pads. Now I'm going to come into my devices right here, and it says I've got no devices. So I need to come in here and I need to create a new device. And I'm going to call that device cap film, because it's got a plastic film in the middle of it. And in here, we've got packages and pins that it's looking for. We can move this window out a little here. It takes a little bit of fussing around. And there we go. We're going to bring in the symbol that we created. So click right up here. And there is our symbol. We want the capacitor, and we'll just say OK. And we will put that right at the origin right in there. And that's got all of that information that we need for the symbol. And just come over here and click on OK, because we're all done. And then we can come down here and we can create a new local package. So we'll click on Add Local Package, and you can see the footprint for your cap film, and we can double click on that right there. And showing up right in there. It's looking rather tiny at the moment, but it's there. And so what we're going to do now is we're going to go ahead and turn on the auto naming, so that it'll give it a name. So if we've got more than one capacitor, it'll say C1 or C2, and use that name value that we've got. And then we're just going to click on connect. And we're going to connect our pins together. Now, because this is a non-polarized device, it doesn't matter which one we connect it to, but if we look really carefully, we should be able to get in here. This one should be showing up a little bit larger. Anyway, we should get a bigger picture of that if it was a bigger device, and we should be able to see the pin numbers. There's 0 and 1 on there, and here we've got 1 and 1. And what we're just going to do is we're going to connect those ones together, and we're going to connect those ones together so that we can see pin 1 goes to pad 1, and pin 2 goes to pad 2, and we're going to click OK right there. And now this is all put together, and we can go ahead and save this. And there we go, it's user saved. And now it's time to go ahead and start creating our project. So what we're going to do is we're going to create a new electronics design. And then we're going to save that as water piano. And again, check to make sure it's going in the right place. And then we are going to create a new schematic. And we are going to save that as water piano. Okay, and now we're going to see if our capacitor works. So we're going to go ahead and we're going to add a part. And you can see Jason's awesome library now shows up in here. And yours might be named something else, so it'll be somewhere else in the hierarchy list. And I'm going to click on Cap Film, and I'm going to say OK. And there we go. I can bring it in right here. I'm going to rotate it around so that it's standing upwards, because looking at our schematic, I'm going to need 2 of those capacitors. I'm going to click OK right there, and I'm going to zoom out a little bit because we're going to need a bit more space when we start adding more things into here. Okay, so we've got our custom capacitors. We can make a custom part. If we want to make sure that we got that all right, what I'd do right now is I would come back to my project right here, and I would try creating a printed circuit board. And on our printed circuit board, there we have our 2 custom capacitor parts right there. So since we're doing this, let's go ahead and save that right now as water piano as well. Now, one of the golden rules about doing your printed circuit design is that you always want to do your editing in the schematic. So anytime you're working on the schematic, you work in the schematic, and then you fire that on up to the printed circuit board, and you edit from there. This window's kind of getting in the way. Let's see if we can minimize that. That pops that window, gets us a bit more screen real estate on here. And then we can zoom out a little bit. Let's add some more components in here. Now, key to making this work is going to be the 555 timer. So let's go ahead and add the 555 timer part. And what you need to search for is star 555 star, which I know what the second star means. It means anything after there. It's a wild card. It doesn't matter. But in here, you can see we've got some 555 timers. Again, watch out for the red pins. Don't pick the red pins. They're surface mount. There we go. There's a through hole one. This is a 555 timer, and looks like it should do the trick for us. Take a look right in here. It changed the DIP package to have round, not oval pin pads. I kind of like the oval pin pads. So you might take a look down and see if there's anything else. These ones are all marked with round pads. So I guess we'll go with a dual inline 8-pin package right here with round pads. Okay, and there we go right in there. Those capacitors are looking awfully massive. We could go back and change that size down a little bit later on. But there is an integrated circuit. Now, one of the things about the integrated circuit, when you look at it in a schematic view, is that the pins aren't shown the same way that they will be on the footprint. On the footprint, there's going to be a notch right up here, or maybe a little dot on this corner, or a specially shaped pad to represent this top corner being pin 1. So you can always find pin 1 because it's going to be just off to the left of the notch or right by the little dot or on the specially shaped pad. And integrated circuit numbering goes 1, 2, 3, 4, 5, 6, 7, 8. Now you can see that that obviously doesn't match the number that we've got in the schematic here. Schematic numbering is often chosen to help illustrate the concepts or to make it easier to hook up the circuit. So these pins right on here, uh, we've got our power and supply right down here at the bottom. They're not that way on the chip. They're at pins 1 and 8. They're actually up at the top of the chip. So anyways, we're not going to worry too much about that right now. We're going to work off the name of each pin. And if they've built the chip correctly, when we translate to the printed circuit board, it should come out okay. Let's add a few more components in here. I just have to pop over to my other screen and bring my schematic back up so I can see what I'm doing right here. And so I've got my schematic displayed on my other screen. You may have downloaded it and printed it out on a sheet of paper to have working in front of you. I always like to have a copy of the schematic somewhere ready to go. And we've got a few things to put together in here. Let's add some parts. We know that the 9-volt battery works out okay if we use AB9V. And let's just say, okay, there is our battery, and we will rotate it so that the positive side is facing up. We'll put it right over here, and we'll want a power switch. So let's come in here and add another part. And that is going to be a single pole, single throw switch. And let's take a look and see what we've got for a single pole, single throw switch. Again, I'm not nuts about their schematics or their footprints for that matter, but it will serve the purpose for what we're doing here today. And let's rotate that around, put that little button on the switch so it's looking upright right there. And there is our switch. And we're good with switches. Let's add a couple of resistors in right here. And we'll go to the RUS and the 0309. The 12 millimeter long ones work pretty nicely. And we'll rotate those so they're in a vertical orientation right here. Those capacitors really are looking rather huge, but like I say, we can go back and edit that up later. It's not going to prevent us from completing this circuit. And what else are we going to need in here? We do need one polarized capacitor over here to go with the speaker, and we do need a speaker. So let's search for speaker, and there's a nice looking speaker right there. I guess it's 5 millimeters across. They're all about the same size. Again, one schematic symbol, multiple footprints. Let's go OK, and we'll rotate that into this orientation right here. We'll put the speaker right over here. We'll say OK. And now let's add in a polarized capacitor. And we'll just search for cap. And a resistor capacitor. Ooh, let's try cap star. See if we get a few more. There we go. And the Adafruit library. C-pole for polarized capacitor. They've got the American polarized capacitors in here. Now we're still getting surface mount devices. Let's see what happens if we turn that off in our search term and search again for cap. C-pole US. Okay, there's an axial capacitor. There's a radial capacitor. Now again, you want to take a look at what size this is going to come out, because this is showing me on the scale that this one is going to be a 10 millimeter body diameter, and we're only looking for a 10 microfarad capacitor. That's closer to a 5 millimeter body diameter. So let's see if we've got something else in here. 12 millimeter body diameter, 12, 27. Let's take a look up under the Adafruit libraries. I think they had something at that one is a 6 millimeter diameter capacitor. with 2.54 millimeter pin spacing. That one right in there, 7 millimeter, 6 millimeter capacitor. That'll do the trick right there. So we'll just say OK, and we'll put that capacitor in right there, because that is a polarized capacitor and pin orientation matters on that, lest you blow the capacitor up. So we've got two film capacitors, two resistors, a 9-volt battery, a switch, a 555 timer, a capacitor, a speaker. Now what we need is some ground symbols to put all of those things together so we can add a part. And let's see what this has available for GND. Okay, power symbols right there. And let's see. There we go. Ground, earth. So you see there's all sorts of different types of ground that are available. And so you can have an earth ground, which if you're building heavy electronics, your chassis would be hooked up to an earth ground, and then you'd have a signal or logic ground inside your circuit. So we'll go with this GND signal right here. And we'll need one for each, not for each resistor, sorry. We'll need them for the capacitors. We'll need them for the battery. I think we need 5 in total. We'll just put 5 in here for the moment, and then we'll tidy them up a little bit later on. Okay, so let's come down right in here, and let's move a few things around. Now to move things, you have to click right on the middle of them. Let's bring this in a bit closer. Let's see, that resistor is going to be in here, and let's take a look at how we hook this up first. So we're going to join some things together right here, and pin 8 and pin 4 go together. So you've got to identify where pin 8 is. That is V positive, and we're going to hook that up to the reset pin. And you'll notice that although I could draw over top of the integrated circuit, I don't. We don't do that sort of thing. It's just like drafting. You never put your dimension lines over top of the object. So we're going to join pin 6 and pin 2 together. Okay, and that is the trigger and the threshold are being joined together right in there. And then our pin 1 is going to come straight down to ground, okay, because that is ground right there. Pin 8 and pin 4, where they join together, come back out to our switch. I'm just going to draw that to that switch for right now. Oh, somehow it joined into our battery. I don't want it joined in there. Let's undo that. Let's bring this switch down into a place where it's going to move a bit better. So I hit escape to get out of that. Click on the switch, move it down, and there we go. That switch will look good right there. Let's move the battery down over here somewhere. Okay, zoom in a little bit and join those two together. I had to click out there to make it turn that way. And then I can connect the downside of the battery to a ground symbol. So I hit escape to stop drawing so I could pick the ground up and move it right into here. And then I'll just draw a net connecting that to ground and make sure it actually connects. If you're ever unsure that it connected, hit escape so you can move things around, pick that up, and if it moves around with it, then it's indeed hooked together. Okay, then pins 2 and 6 just connect to each other, and then they come out of there and they come to one of the resistors. So that comes out of here and it's going to come down to a resistor. And that resistor is going to have to move inwards a little bit right there. Move that point in a little bit. Move this resistor inside from that a little bit as well. Those two resistors are going to come out to our terminals. Pin 5 is going to come to a capacitor and then go to ground. Here's our strangely huge capacitors. Oh, they're taking up so much space. Bad capacitor design. Let's bring this out over here a little bit and try not to have, I'm just going to delete that for a second because it's easier to redraw a net right in here, and we try not to have angled or strange nets happening right when we're drawing the schematic. It's fine on the printed circuit board, but on the schematic we try to keep things reasonably neat and tidy. Okay, and pin 5 is going to come to a capacitor, and it's going to come to ground. That's moving the ground around. I don't want to move that. I want to move the actual ground. I'm going to drag that capacitor down there a little bit so it's a bit out of the way. And pin 5 takes a net, comes out of there, and then that capacitor comes down to ground. And our other capacitor is going to be over on this side. Whoops, not drawing nets right now. Hit escape and drag that capacitor around right over here because that capacitor is going to come to ground on the other side of where R1 connects. Right there. And R2 is going to come up to our power on that side. And then pin 7 is going to come over and connect on the downside of that. All right, we've got one more ground left here. We've used 3 of them so far, and we said we were going to need 5. And let's take this one right here. Stop drawing your lines. I've got to hit escape. Bring that down over there and connect right there. And there's that spare ground that we brought in. Hit escape so I can move that over here. And our speaker is going to come out this way. And our speaker gets its output from pin 3. Okay, that's all coming together right there. Then pin 7 is the one that comes around and on the downside of one of these capacitors. Now these capacitors need, or sorry, these resistors. These resistors need a way that they can get their wires off the board. So for that, we need to bring in a little header for them. A header is just a place where we can connect an external wire. We could just bring in a pad as well, but let's put in a header and it'll look like a header pin. We can use a wire if we want to. So we've got to add one more part. Okay, and let's just look for header, see if they give us a pin header 1 by 1. There we go. And click on the down arrow because you can see we don't have a footprint for it right there. And there we have a footprint right there. There's one with a nice big pad. And let's use one with a nice big pad. So we got lots of copper to solder it to. And we'll bring that in right here. And let's rotate it opposite direction. And let's put that one right in here and that one right there because that's where those wires that we're going to touch are going out. And we're all done with that. Cancel that. We're all done. Okay. And now let's connect. Where do they want this one to connect to? Right there. And we want to connect from right here to right here. Okay, so now we want to go back and double check and make sure that our circuit is all hooked up. Oh, I see one thing missing over there. Okay, before I go and fix that, I'm going to hit escape so I can move things around. Sometimes I have to hit escape twice. I'm going to bring all my grounds down here just for these strangely large capacitors that we built. They didn't look that big when we were building them, but okay, they'll work in there. And now pin 7, looking at the original schematic, comes to the intersection between R2, which is hooked up right there, and ground. So we're going to add pin 7 down here and bring it right over to there, and that joins in right there. Okay, now this schematic needs a little bit of tidying up. Well, there we go. It's not the prettiest schematic that I've ever made. I'm not particularly fond of how this chip is set up. I might redesign that for my own purposes later on, and I think I kind of botched it on making the capacitors a little bit bigger than the symbol needed to be. But live and learn. If you're using this for the first time and you're looking at that saying, "Wow, he's really struggling with that interface," I've been using a different package called Design Spark PCB for the last 10 years, and it's been working great. I'm very familiar with its interface, but we've switched over to this one because it is compatible with Macs and PCs. So there we go. We've got a schematic all ready to go. Let's save it up. And then let's come back to our project right here, and our schematic shows up right in here. And now we already earlier created a printed circuit board. Well, our schematics changed a lot since we had that printed circuit board created right in here. And let's go ahead and create the water piano. Come over here to the water piano board, and it should update for us. There we go. Everything's updated and our components are all down here. And you can move them up onto your board and go ahead and begin your routing. Have fun. We'll see how it goes.